Okay, friends, in our previous lecture, we have seen that how to write the difference equations of the in place of original differential equations. Now we are going to use the finite difference method for applying these equations for solving the plate problems. Now we have seen that in fourth order governing differential equations which will behave the plate in bending, uh, it is written as equation 1, and alternatively we have also seen that it can be replaced with two equations in terms of moment and deflection, in terms of load and in terms of moment, second order partial differential equations. Now what finite difference equations that we have derived in our previous lectures, we are going to substitute that into our equation 1, and then simplifying we consider the same grid which we have taken as earlier. We will get this equation, and please understand this equation is written at point O of the grid. Point O is, it is shown in the next slide. That point O is somewhere here, and we have written one equation in terms of fourth order differential equation. Similarly, we can also write the second order partial differential equations equivalent to finite difference equations at point O is like this. These are the two equations. Now to get the solution, we can write this equation at each and every node or point, and in the entire process, we'll get the simultaneous algebraic equation similar to these. Like this is one equation written at point O, similar to this we can get the similar equation at every other nodes, and we will get the simultaneous equation numbers as equal as the number of nodes unless some symmetry condition is applied, that we will see later on. And solution of this simultaneous algebraic equation gives us actually the values of moment at the nodal points and values of the deflection at the nodal points. We also have to understand that these equations along with the boundary conditions are also written in terms of difference equations, and we can incorporate that boundary equations, difference equations in these equations, and we can simplify. So basically these equations have to satisfy the governing differential equation as well as the boundary conditions for solving the problem. Now consider one example. Of the simply supported square plate at all edges, and since the all edges are simply supported, we can, and also the uniformly distributed load is applied, so we can assume that this plate can be analyzed by applying the conditions of symmetry. So only, you can see here, only 1/8 of the portion of the plate can be analyzed. This idea of applying symmetry condition is to reduce the effort, reduce the equations, simplifying the equations, because you know that whatever moment and deflection value you are getting here will be same as the moment value and deflection value, same as here, same as here, same as here. Similarly, symmetry conditions apply for node 2 as well, node 3. So we are going to write our finite difference equations at node 1, 2 and 3, and those equations are sufficient enough to give us our final values of the moment and the deflection. So we start with this partial differential equation simultaneous because this is easier to solve. These equations are easier to solve because why it is easier to solve? Because it's a second order, simple. So writing this first equation, this is our original equation of second order differential finite difference equation. Now writing finite difference at node 1 here in the direction x. Okay, node 1 in the direction x. We simply use this equation, donate the nodal values, because this is written in general standard format. We convert that into our moment and deflection values, designate some values of moment and deflection. This is nothing but the function, deflection is nothing but function. So functions values are being replaced with the function what we want. So we will replace yn as m1 because I want value of m1 here. Then forward values yn plus 1 will be here, that is m2, and yn minus 1 is the left hand point, will be somewhere at the left. Now you can see this left point of this node, that is yn minus 1 in the x direction, and this is nothing but boundary point. So I know that on the boundary, all four boundaries, and because of symmetry, of course this value may be because of symmetry, and the deflections and the moments will be 0. So I have written over here is 0. You can substitute these values into this equation and you get this. Now similar equation we are writing in y direction. You can check yourself here in y direction. So yn plus 1, yn minus 1 and yn is, because we are writing our equation at node 1, yn is written as at m1, yn plus 1 is again in y direction. You can see n plus 1 value will be somewhere here, it will be somewhere here, and it is nothing but, in this case it is somewhere here, it is a boundary point. So you can make it 0, and yn minus 1 is in y direction is this point. Because of symmetry, this point is same. As I have mentioned, the blue numbers are symmetrical points where your deflection value will be same as moment value and deflection value, same here at node 2, same else. So I will write here symmetry point m2 and yn is equal to m1. Substituting this, we are getting this equation, and because we need to add this, so we are going to add equation 1 and 2, and we know that size of the grid, that is h is equal to a by 4. We substitute h square, so a square by 16, and we get our differential equation in terms of difference equation. This is written at node 1. Now we are going to write similar equation at node 2. So we follow the similar approach. Writing at equation at node 2, I have shown this grid. You can think of node 2 at the center, that is yn. You put value of moment at m2, then right side, left side, when writing in x direction, the forward and backward values. One of the value will be symmetry, I have written here. You can write m1, it is same as value at node 1, then boundary value, and here there is no boundary value which is there when we are writing in x direction, and value forward, backward, and the value at 2, and summing up. I mean writing that equation into difference equation. Similarly, we are writing in y direction. So yn is m2 in y direction. Yn minus 1 is m3, and forward point yn plus 1 is matching at the boundary. You can make it 0, and in the process we are able to write this equation too. Summing up these two equations, we are getting this equation. Similarly, we are writing at node 3. You can see our original diagram and expand this node 3 to look at the values. So at node 3, when you are writing equation, just write forward values, backward values in x direction, y direction. We are getting this value, we are getting these values. Just summing up 1 and 2, we are getting this final equation. So together we can write these three equations of moment. These three are simultaneous equations. So you can see here one of the equations not having m3, and you can solve this equation by hand by substituting m1 into this equation, and you get all your equation in terms of m2 and m3, and these two equations later on you can solve. Or you can adapt any other method for solving the simultaneous equation. When you solve, you are going to get this m1, m2, m3, your moment values at that particular points, and also at the symmetry points where these values are matching and the same. Now similar approach we have to follow for the second partial differential equation, that is I have shown earlier, which is here. This equation also can be written in a similar. You can see some similarities here. Both equations are same except the values of m and w. So difference, when you write difference equation at same nodal points, the things that equation remains same except we are writing w1, 2, 3 instead of m1, m2, m3. So the right hand side is different. We can write instead, when we are writing at node 1, here you can, instead of m, you can write m1, then m2 when you are writing an equation at node 2, m3 and you are writing equation at node 3. So our final equation, for you can see the similar equations except the right hand side where we have substituted m1, m2, m3 values. Second equation is very similar except the right hand side. Third equation is very similar. Now again we solve these three equations to get the values of